Welcome to this third video in the series The Road to Quantum Reality. The title, Doing the Sums, is of course partially facetious, but it is actually quite a relevant one because to a large extent we are simply adding waves together. You might recall this animation from the last video, which showed waves emanating from a grid of vortices. By the way, I have used the general expression vortex or vortices up to now, but in developing and writing about the theory, I personally used the term field rotators to describe them, and shortened this to FR. So from now on I shall start calling the vortices FRs. Anyway, back to the grid. The first thing to say is that we have absolutely no reason to surmise that a stable structure of FRs should be in a grid or cubic state. Indeed, the expectation would be that as there are different fundamental particles, there will be different self-supporting structural forms. But grids are at least a possibility and offer the advantage that they are easy to perform calculations upon. So all the work described in this series of videos is based on 1, 2 or 3D rectangular lattices. The results seem to imply that this is the correct structure for the electron and positron. As was noted in the last video, the spiral waves travelling along the axes arrive at the next FR in phase, while those at an angle do not. For example, look at the blue wave travelling to the lower left FR. We want to apply our postulate that the gain at an FR is proportional to the present amplitude and the local gain field. But how do we know what the FR amplitude is? The waves are coming from different directions and have different phases because of the distances they have to travel. It seems like a mess of constructive and destructive interference. At first sight, it appears there could be some parallel with Feynman's sum over all paths methodology, by which he was independently able to derive Schrodinger's equation. Part of this methodology is to add contributions from every possible path in space-time leading to a particular point in space-time. Each contribution is represented by a complex number, representing a phase and a magnitude, and the method used is vector addition in the complex plane. The process is illustrated here. The red arrow is the final phase and amplitude for the point in space-time. We also need to add complex numbers, but in our case they represent physical phases and amplitudes rather than probability amplitudes. However, if we try it, we run into an immediate problem. Looking at our 4-wave prototype, at an instant in time the waves have the same magnitude but 4 different phases separated by pi by 2. If we add the vectors, we just go round the square and get back to 0. This is because the point to which we are trying to attribute a measure of angular momentum is actually a node, as can be seen by looking at the animation. Our problem is that we are concerned not only with the phase, but also with the direction from which the wave approaches. The Feynman summation takes no account of this. To come up with a better method, let's start by looking at a prototype plane wave. We are using the standard form that the phase of the wave is given by kx minus omega t. We can represent such a wave by the top arrow in this figure. The direction of propagation is given by the arrow. Notice that because the phase contains positive kx, the phase increases with x. We have written the position of phase 0, pi by 2, pi and 3 pi by 2 beside the arrows. In fact, the phase will continue to increase in the x direction, so the next step would be 5 pi by 2. But we are not going to get involved in bigger or smaller phases by only considering phase as modulo 2 pi. In other words, 5 pi by 2 becomes pi by 2 and minus pi by 2 becomes 3 pi by 2. The lower arrow in the figure is a picture some short time later. The wave has moved in the direction of the arrow. Looking at the point indicated by the red line, we can see that the phase has changed from pi to something a bit less than pi. And this is what the negative t means in the phase equation. Phase at a fixed point reduces with time. Armed with this picture, we can examine the 4-wave node in more detail. We start with the wave progression we have been illustrating, with the wave directions being progressively from the north, west, south and east, or travelling south, east, north, west. This can be confusing, especially if, like me, you have done some sailing, when a north wind is from the north, but the air is moving south. The arrows in the top left give the progression we are actually examining. Let's start with the wave direction shown by the yellow arrow, and let's focus on an instant of time when its phase at the point under consideration, that is the node, is 0. We can fill in the first row of the table. The wave direction is 3 pi by 2 and its phase we have just set to 0. Now we want a measure that takes the direction into account, so let's consider the alternatives. As one alternative, let's add the phase to the direction, and for a second alternative, let's subtract it from the direction. We put these values into the last two columns. They happen to be the same in this case, 3 pi divided by 2. Now we move on to the next wave direction shown by the arrow. We want the phase of this wave to be 0 in a quarter of a cycle's time, so at the present moment it must have phase pi by 2. Remember, phase at a point reduces with time. Now, filling in the table with direction 0, we get the sum of pi by 2 and the difference 3 pi by 2. Remember, we are operating modulo 2 pi, so 0 minus pi by 2 is 3 pi by 2. We apply the same principle to the next wave direction of pi by 2, noting that the 0 phase must arrive in half a cycle's time, so it must currently have phase pi. The sum and difference are now both 3 pi by 2. Finally, with wave direction pi, we have phase 3 pi by 2, and the sum and difference are pi by 2 and 3 pi by 2 respectively. Now each of our waves must be contributing equally to the spin. So the measure we want must be to take the difference between the direction and the phase, as these all give a vector pointing in the 3 pi by 2 direction at this instant of time. Next, we look at a small instant of time later, say delta. Remembering that the phase at a point decreases with time, we can put in the reduced phase as shown in column 2 in this figure. As our measure takes the difference between direction and phase, this means that the direction of all the contribution vectors must increase by delta, which corresponds to the mathematically positive spin direction, which is what we want. Now we can play the same game with the reverse direction of spin, with the direction sequence as shown by the small red arrows in the top left. The first row of the table is the same. The second row shows that the sum is 3 pi by 2 and the difference is pi by 2. The third row is the same as for the opposite spin, and the fourth row again has sum 3 pi by 2 and difference pi by 2. So this time it is the summed direction and phase which gives 4 equal contributions to the spin. Once again we can confirm the spin direction by considering a small time delta later. The phases are all later by delta as before, but as we are summing direction and phase, the sum is also reduced, represented by the 4 contribution arrows being rotated clockwise, so mathematically spin negative. In summary, we have developed 2 different discrimination processes. If we subtract phase from direction, we get a measure of positive spin. If we add direction and phase, we get a measure of negative spin. In both cases, we sum the contributions, much like the Feynman sum, but now we get a final value for spin, phase and magnitude at an FR. There are some caveats to this approach. The first, and perhaps the least worrying, is that the waves are actually spiral rather than plane, so waves from nearby FRs will be a bit curved. The second is that discriminators are only valid if waves are coming from a balanced set of directions. As an extreme example, if we applied discriminators to the node of a standing wave, we would get a strong result even though no spin could possibly be present. Actually, even in FRs embedded in a smooth structure, there would probably be a degree of inaccuracy in the estimate of angular momentum because of the presence of a gradient in the magnitude. In this sense, the discriminators are our best estimate of the angular momentum without going into deeper detail. So on balance, we can see where this leads us and bear in mind that what we might find may not be strictly quantitative but can still be qualitative, and this will still give the insights we are seeking. Okay, so that's the theory. Now, how do we put it into practice? We need to calculate the phase and amplitude of a contribution from a source FR to a target FR, which can have any relative position in space. This is going to lead to a very surprising and important conclusion. First, let's look at positive spin, that is, spin in the anti-clockwise direction. In this figure, we show a source FR positioned at S and 2 target FRs, the first at A and the second at T. To keep things simple, we make the distance of each target from the source exactly 1 wavelength. That is, both A and T sit on the dotted circle. The red spiral indicates the 2 pi phase line for the source FR. It is shown having a phase angle of 0, so the 2 pi point on the wave has just reached point A. The orange line is a phase indicator line like the ones we used earlier. Now, if we look at the target T at the same time, it is clear that it is further along the orange phase marker line, so it must have a greater phase. Remember, phase increases along the direction of the wave. Look back at the earlier slides if this feels confusing. A little further thought makes it clear that the amount of extra phase is exactly theta st, because if we move the target right round the circle and back to A, we get 2 pi, or equivalently 0, which is what we already know it must be. Now we can think about having the target further away than one wavelength. The phase at A, for example, would be just the distance divided by the wavelength. The greater the distance, the greater the phase. But this will have no effect on the directional element of the phase. So we have that the phase arriving at the target, say small phi t, is the sum of the distance component, capital Phi st, and the source target angle, theta st. Now apply the discriminator for positive spin, which is direction minus phase. And note that the thetas cancel, so the phase only depends on the distance from the target. In other words, it is independent of the direction of the waves. Looking at negative spin, the spiral is reversed, and following the same line of reasoning, we can see that the phase arriving at the target is less than 2 pi by the amount theta st. But the negative discriminator is the sum of the direction and phase, which means the angular component again cancels, and we get the arriving phase is just d over lambda, so again independent of the relative location angle. Let's just recap what happened. First, we showed that the Feynman sum was not appropriate because it did not take direction into account. But note that in reaching this conclusion, we did take direction into account. Then we developed the form of the discriminators, which took the direction of spin into account. And when we applied them, we found that directional variations cancelled out, and we were left once again with what was essentially the Feynman sum. From our perspective, Feynman makes two errors by ignoring the spiral wave and ignoring the direction. These two errors just cancel out. We conclude that our discrimination process is just a discrete form of the Feynman sum, apart from the 1 over d factor. And we note that in reality, path integrals are usually calculated on discrete grids in what is known as effective field theory. The choice of grid size does not ultimately affect the results. We are just saying that a grid size of the Compton wavelength is in fact physically meaningful. In summary, our kernel for time-independent, that is stationary, states can be summarized by the equation in green. And here I show two Python code snippets used in the computational work. Thanks if you've made it this far, and sorry if it has been a bit dry. In the next video, we will apply our theory to a single dimension and get our first results. When I did this work, it was a bit of an emotional roller coaster for reasons that will become apparent. Meanwhile, here is another 3D structure calculated using real-wave quantum mechanics.